plasma.
And it's under these extreme conditions that something really, really cool happens. Nuclear fusion.
It's the same atomic process inside the hydrogen bomb. Under tremendous pressure, protons in the plasma fuse together, releasing photons, minuscule packets of heat and light. An unimaginable number of photons are made every second, generating the sun's incredible power, some of which reaches us as sunlight. This atomic alchemy converts over 4 million tons of mass into energy every second in an endless loop.
That much mass into energy is the equivalent of 10 billion hydrogen bombs being created every second. The sun does this day in, day out. It's been doing it for 4 billion years, and it's going to continue to do so long after I'm gone.
The energy of billions of bombs is released in the core every second. This begs a simple question.
So you could ask, well, why doesn't the sun blow itself apart? It's because there's this beautiful balancing act that occurs. In the core of the sun, you've got this pressure from all of this fusion pushing outwards. And the sun is huge, so you have all this gravitational pressure pushing downwards. And so you've got gravity pushing down, and the sun trying to blow itself apart from the inside, and it is this beautiful balancing act between the two that keeps the sun in one piece.
This light, born at the core, reaches us after a remarkable journey. Away from the core, pressure and temperatures drop, and nuclear fusion stops. Now, each photon begins a tedious journey through the sun's thickest layer of plasma, a region called the radiative zone. Although squeezed less than at the sun's center, the plasma is still very dense, and photons struggle to move through it. Each packet of energy is continuously absorbed, then spit out by the plasma particles.
In that particular part, there's no energy being generated, but the energy is transmitted by the radiation. So that's why we call it the radiative zone, not too surprisingly.
The photons slowly bounce through the plasma here, ricocheting in a zigzag path called the random walk.
So imagine that you're in a crowded room and you're trying to make your way through, and you greet other people. And each person you greet, you have to say hello to, and then you move off in another direction. So it takes you a long time to get from one place in the room to another because you're just kind of meandering your way around the room. So the same way the photons in the inside of the sun, they don't have a preferred direction. All they want to do is they want to be moving, and they want to be greeting other particles.
Though moving at the speed of light, 186,000 miles a second, it takes photons over 100,000 years to cross the zone. Eventually, the photons reach a boundary where pressures drop again. The plasma thins, and moving through it gets easier. The photons still pack a lot of energy. Now, they leak out into the convection zone, heating it from below. The thinner plasma in this zone makes the photons move in a different way.
So instead of bouncing, all of a sudden there's an ordered motion. So it's as if all of a sudden someone said, lunch, and all the particles decided, oh, we all have to go this direction. And you still have to wait in line to get out, so it takes a month to get from the bottom of the convection zone to the surface, but it's a relatively short period.
During this short period, Heat from the photons sends plasma here into perpetual motion, a maelstrom of churning 125,000 miles thick. Think of it like a massive lava lamp.
There's heat that enters at the bottom from the light bulb. It heats the material, and the blob rises to the surface. When it gets to the top, it cools off. And when it cools, it gets more dense and falls back down. This is a good analogy for what's happening inside the sun. We have the core of the sun heating the material at the bottom of the convection zone. The material expands, and it carries the energy upward until it gets to the surface.
These incredible images reveal convection at the sun's surface, rising and sinking plasma that creates a mesmerizing structure called granulation.
The granulation cells are about the size of the state of Texas. They only last for about 12 minutes, so there's an incredible amount of energy. It's a very dynamic, very chaotic place. And all of the activity is going on the surface of the sun where we can see it.
Photons produced at the core finally reach the surface. They emerge as a weakened form of solar energy. This weakened energy reaches Earth in 8 minutes. We know it as sunlight.
So 100,000 years, about a month, and then 8 minutes. Once you get to the surface of the sun, it just takes 8 minutes to get to where you can see it.
Unimpeded, the trip from the core to the surface would take the photons a matter of seconds. In reality, the sunlight that shines on us today may have been created during the last ice age. Energy reaching the sun's surface doesn't just result in sunlight. It can also trigger solar storms. Understanding the sun's destructive power requires 24-hour precision surveillance, something that, until recently, was impossible to achieve.
5, 4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were going to open our doors to actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed a portion of the sun in high resolution. Now they see it in mind-boggling detail.
Now, in order to look at the Solar Dynamics Observatory images that we're bringing in every day, we've built this very special wall, which is 9 high-definition television screens together that can display these images, so that the instrument and the display system together are an entirely new way of looking at the sun.
We can see all the details of what is going on, and that is really a quantum leap in solar physics. Being able to see all of that all the time, a continuous eye on the sun.
One of the most important aspects of SDO is its ability to see sunlight across a range of wavelengths, the equivalent of looking at things glowing at different temperatures. Our eyes are most sensitive to sunlight glowing at around 10,000 degrees Fahrenheit. At this temperature, the sun's surface looks almost featureless. But at hotter wavelengths, normally invisible, a far more dynamic picture emerges. The February 15, 2011 storm is a perfect example. In this repeating image, at around 90,000 degrees Fahrenheit, SDO captures just a ghostly trace of the CME wave. But at just over 1,000,000 degrees, the superhot plasma rippling away from the eye of the storm is much clearer. This allows researchers to see coronal mass ejection waves evolving across the entire sun.
This is an absolutely amazing time for solar physics because of these beautiful high-resolution images that allow us to understand better the physics behind what's going on when solar storms erupt.
Was that one last photo? Look at this one here.
Back at the National Space Weather Prediction Center,
That's the M1 here.
Bill Murtaugh tracks the storm's CME wave. It carries 1 billion tons of plasma and is now only about 20 hours from Earth.
We're bringing it in mid to late on the 17th into the 18th.
What they see is alarming.
Well, there's actually 3 CMEs that we're looking at. So we bumped up some numbers for late tomorrow. Yeah.
It's not a single CME wave, but 1, 2, 3 of them.
We won't call it the perfect storm yet or anything, but conditions are lining up for some significant space weather.
Their models show trajectory and speed, but the big unknown for Murtaugh is how powerful the waves will be when they hit. The answer lies in a force that governs the sun: magnetism. We're all familiar with magnets. They produce an invisible force that pushes and pulls on charged particles. In fact, Earth has a magnetic field that protects us against threats from the sun. But we are less familiar with the sun's magnetic power, which researchers believe plays a major role in driving solar storms.
We've essentially learned that it takes 2 things to make a star magnetic. It needs to have these convective motions right underneath the surface, the bubbling of the gas. It needs to spin, and the faster it spins, the more active it becomes. And wherever those 2 things, the bubbling and the spinning, can interact, that's where we see the strongest magnetic activity in stars.
Astronomers know that the surface of the sun spins in a strange way. Travel from the poles of the sun towards its equator, and you'd notice it turns faster. Analyzing sound waves inside the sun reveals that the plasma layers beneath the surface also spin.